Hello everyone and welcome back to the Inorganic Tutors Institute. My name is Nasiruddin Gati, your tutor for actuarial science and probability courses. So in this lesson, we are going to solve some questions under the concepts that we saw in lecture 1. So we are going to solve questions across events, knowing the sample space, and calculating basic probabilities. This part of the course is very crucial as it forms the basis of all the probability concepts or theories you'll be studying ahead. So it's very important to make sure you understand, watch the entire video, and abreast yourself with how they are being solved. So let's kickstart and see what we have for today. So for each page there is a question. You might pause to try it on your own, then later on we solve it together. That's when you have the time to do so. Otherwise, I can walk you through, then later you take the time and take them one after the other. Each of them is good, but it's advisable that the ones you feel you can solve, you pause and try your hands on them. So let's start for the day. So the first set of questions we have are theory questions. Let's see how we can best answer them. So you can pause and give it a try on your own. So we have define the following terms in your own words. Yes, something trying to see how best you understand the concepts. So we have random experiments. So we saw the last time that an experiment is random if one, its outcomes are well known or are well defined. You know all the outcomes of the experiment or of the activity. And 2, the outcome of the experiment cannot be determined with 100% accuracy unless or until the experiment is done. So before conducting the experiment, you know the set of possible outcomes, but you don't know which one is going to show up. Before you toss a die, you know that you either get a head or a tail, but you can't tell the outcome you get until you are done rolling the die. So that's what we mean by a random experiment. The second item you have here is a simple event. Remember from the previous lecture that we said a simple event is one that has just one outcome from the sample space. So it consists of doing just one thing. So when we have rolling a die, we have either getting a 6, which is just one outcome, or getting a 2, which is one outcome, or getting a 4, which is one outcome. So an event that has just one outcome is what we call a simple event. On the other hand, a compound event is one that has 2 or more outcomes from the sample space. Okay, so when you roll a die, the chance of getting or the event of getting an even number is compound because it doesn't consist of just one event. Getting an even number is not restricted to one outcome in the sample space. You can get a 2, you can get a 4, you can get a 6. So once we have 2 or more outcomes from the sample space, we call it a compound event. So I believe these 3 terms are well understood as they should be. So we proceed to the next set of questions. We have also a theory question. State and explain the two fundamental properties of probability. Give an example for each. So we are asking about the fundamental properties of probability. So we saw last week that first, any probability that you obtain should be between what? 0 and what? 1. And I remember telling you that the worst case is a 0. If the event is not possible at all, there is no way, there is no chance that it might happen, we give it a 0. And if we are very, very sure, imagine there are 5 balls in a bag and you are going to pick one, and they're asking you what's the probability that you get a red ball. Remember, all the balls are red in the bag, so the chance of getting a red ball is sure, it's certain. In that case, we assign a probability of 1 if the event is certain. Okay, so there's no way the probability would lie outside this range. When you solve a question, you get probability to be 4.5, to be -3, to be 6.9. Know that the answer is wrong. So give an example for each. We can say probability of E equals maybe 2/5, or probability of E equals 0.9. You might also see in percentage 70%. Yes, these are all ways to write probability, and these values are all within 0 and 1. Okay, now let's see what the second property is. It states that when you sum the probabilities for all the events, you should get 1. Let me see all events. So when you sum for all events, it should give you 1. So what do I mean by events here? So, okay, maybe I should put it well and carefully. Yes. So when you sum all the simple events, yes, it should give you 1, not all events. Because we can define events in such a way that you sum and it will be 1. Let me give you an example. If I say first event is that you get an even number from a roll of a die, that's 2 forces. And the second one could be getting a number less than 6, which is 1, 2, 3, 4, 5, 4, and 5. So the first event is getting an even number. The second event is a number less than 6. Remember, the first event will give us a probability of 3 out of 6. And the second one will give us, because there are 5 outcomes, to give us 5 out of 6. Now when you sum 3/6 and 5/6, you get 8/6, which is more than 1. So it's incorrect to say that the sum of all events is the sum of all simple events should give us 1. So in view of that, it means if you have 1, 2, 3, 4, 5, 6 from a roll of a die, the sum of the simple event, so the first simple event is what? 1. The second simple event is 2. third simple event is 3. In that order, up to 6. Okay, so the probability of the first one, because it has one outcome, is 1 over 6. Because this has one outcome, don't go and write 2 over 6, please. It has just one outcome. You are not looking at the value in, you are looking at the number of outcomes. It's just one. So this will also give us 1 over 6. This will give us 1 over 6. This will give us 1 over 6. And the ones in between, the 4 and 5, will also give us 1 over 6. So when you sum the simple events, it will give you a total of 6 over 6, which is 1. So the sum of all simple events, or the sum of the probability of each outcome, when you sum them, you should get 6. So that's the second property of probability. Okay. Now we can move on to the next question we have. Okay, it's asking us to give an example for each. Okay, basically I dealt with each of them in a way that I have presented an example, so there's no need for another one. So the first one I wrote 2 over 5, 0.9, 70%. They are all examples of probability within 0 and 1. In the second one, I gave you a nice example where I illustrated the row of a die. Then I had each of the probability being 1 over 6. Summing them will give you a 6 over 6. So these are the examples. So we move on to the next question. We have also a theory question. Explain the difference between theoretical probability and experimental probability. Give an example. So remember, in the last lecture that we had, we demonstrated that theoretical probability is the same as classical probability, where we assume that for the theoretical, we assume that all outcomes are equally likely. Okay, all outcomes are equally likely. And let me give an example. So when you have a roll of a die, yes, I really like rolling a die because that's one basic example we use in probability for easy understanding, because we all know how rolling a die behaves. Okay, so with something like this, when you are rolling a die, all the outcomes are equally likely. The chance that you get a 3 is the same chance that you get a 6. It's the same chance that you get a 1. Okay, that's what we mean by all the probabilities, all the outcomes are equally likely. This is restricted to theoretical or classical probability. That's the assumption, and that's the example I have given. Also, in a toss of a coin, the outcomes are equally likely. Head, tail, 50-50 chances. Okay, that's what we mean there too. Now, we look at the second one, which is experimental probability. We say this one is based on what we observe. Okay, this type of probability is based on past data, what we have observed over a period. So I gave a nice example last week that let's assume I roll, or let's assume I'm picking a ball from a confinement. Some are red and some are black. So I do the first picking, I get a red, I get another red, I get a black, I pick again, I get red. They are all at random. I get another red, I get another red, I get another red, I get a black, a red. I want to pick 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. And the last one is, say, red again. Now they ask you, what is the probability of selecting a red? Okay, in this case, you wouldn't say red and black have 50-50 chance. although they are just two, this is not theoretical probability. We don't assume that the chance of red is the same as chance of black, but we look at what the data is saying. So from this data, you ask yourself, how many red have we obtained so far? That is 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 red out of a total of 10. So we can conclude that, oh, the probability of getting red is 8 over 10 or 80% or 0.8. Okay. So although we have just red and black, we don't assign equal probabilities to them, but we look at the data that we have. So someone can do to get a better probability. Remember I told you we will do it for a long period of time for us to know the correct probability. Okay, so yes, this is how the experimental or the empirical probability behaves. It looks at the data, but for the theoretical, we don't have time to look at the data. We just assume that they are all equally likely to happen. So when there are two outcomes, we give them 50-50. When there are 4 outcomes, we give each of them 25% chance, or 1 over 4, 1 over 4, 1 over 4, 1 over 4. Okay, sure. So we can move on to the next question, which I'm not sure is a theory question. Yes, it isn't a theory question. So let's start with some practical questions. By the way, there are 10 questions in all. Sorry for not mentioning that. There are 10 questions in all. So we are currently on the 4th question, 6 more ahead. So let's tackle this question nicely. A bag contains 2 red, 3 green, and 1 blue marble. 1 marble is drawn. Let D be the event of, or let D be drawing a red or green marble. When you see a statement like let D be drawing a red or green marble or any other thing, it means let D be the event of this happening. So let D be the situation where we will get a red or green. Okay, let D be the event that we will get a red or green. So when they want to write it in probability, then they can write let D be drawing a red or green marble. So just take note of that. So the first question is, list the sample space. We saw a similar thing in the previous lecture. Let me repeat that. List the sample space. Remember, I told you it is wrong. It is wrong because it's wrong. Let me use red. It is wrong to write sample space equals red, green, blue. No. Although you can either get a red or a green or a blue. That's the situation or the outcome that you get. You either get a red marble or a green marble or a blue marble. That's the situation. But we do not write it like this. Okay, we treat each marble distinctly. Okay, so instead we have sample space equals the first red ball, the second red ball, the first green ball, the second green ball, the third green ball, and the only, sorry if I mentioned ball, and the only blue marble. So this is the correct sample space. The number of sample space, remember, should be equal to the total number of items we have there. So if you do the previous one, you get number of sample space is 3, and all your workings will be wrong. The number of sample space should be equal to the items that we have or the marbles present here. So if you do your sample space and the number of sample space is not equal to the total number of items you have there, there is a problem. Please take note of this. So in this case, when we list each of the items distinctively, so you label them first red, second red, first green, second green, third green, the only blue marble. So the number of sample space here becomes 6. Well, they didn't ask us for the number of sample space, but I'm putting it down for you to understand and also to aid us in question number 4, where we will find a probability. Okay, sorry, that's not a probability. Okay, sorry. So I'm just putting it there for you to understand. Okay, sure. So that's the how to write the sample space. Now, the second one is identify a simple event, which we saw in the previous lesson. So D, so a simple event could be B, or the event of getting a blue ball. The event of getting a blue ball. Or another one, the event of getting the first red ball. Without the first, you are wrong. It's not the event of getting a red ball. It's the event of getting the first red ball. If you say red ball, there are 2 outcomes. Either the first red ball or the second red ball. They are all red balls. So to be safe, you either go for the event of getting a blue ball, which is just 1, or you correctly say the event of taking the first red marble. Sorry about the ball. First red marble. Okay, good. So we also have identify a compound event. So the event of getting more than 1 outcome. So we can have getting the event of getting a red marble. So when you say red marble, it's either the first one or the second one. That is correct. Or the event of getting a green marble. So the first green or the second green or the third green. That's the event. Or the event of getting a blue marble or a red marble. This how this will look like. We will do more of these in the coming questions. So I said event of getting a blue marble, or if not blue, you will take red like that. So this is event of blue marble or red marble. So any of these satisfies. Okay. Any of these 3 marbles satisfies the condition. Okay, good. So that's how to state a compound event. And the last question, we said we should find D. Remember, D is an event, not a probability. Let D be drawing a red or green marble. If they want it to be probability, they will say let D be the probability, but this is let D be this. So D is only an event. So you can just list it as an event, and an event is a set. Okay, not a probability. So the event is drawing a red or green marble. So either you draw the first red marble or the second one, or the first green, or the second green, or the third green. So this is D. Okay, this is D. Red or green marble. So either the first 2 red or the first 3 green marbles. They all satisfy the event. So if I'm to add something small that maybe we should add the probability of D, it will be the number of D, or the number of outcomes in D, which we can clearly see as 5, over the number of sample space, which is what? 6. So getting red or green marble is 5 out of 6, and clearly you have 5 of them, and just one being blue. So if you want red or green, then you have a 5/6 chance of succeeding or getting that. Okay, so that's how to go about with this one. Let's proceed to the next question. Okay, so this is where things starts becoming a bit technical, and you really need this. Once you don't these concepts are not clear to you, you might struggle in a probability journey. Yes, you might struggle a bit in a probability journey. So bear with me, work with me, and let's get this done. A coin is tossed and a die is rolled. So we have two activities going on here. We toss the coin and we also roll the die, all at the same time. Okay, so let A be head appears and die shows an even number. Let A be head appears and die shows an even number. So first we are to list the sample space, and sample space is always important because that's what you use to determine your probability. So whether you are asked or not, you have to clearly state the sample space for the question. So list the sample space. So you think about the outcomes. But before we do that, let me give you this clue that you would be working with most times. When you are to get the sample space for two different activities or experiments, remember this, we are rolling a die and we are also tossing a coin. To be safe, have the number of outcomes in the sample space at the back of your mind. Have the number of outcomes in the sample space at the back of your mind. And to easily determine the number, multiplying the number of outcomes for each of the activities. Multiplying the number of outcomes for each of the activities. So a coin is tossed. When you toss a coin, what is the number of outcomes? 2, head or tail. Okay, 2, head or tail. When you roll a die, what is the number of outcomes? 6. 1, 2, 3, 4, 5, or what? 6. So the number of outcomes are 6. Okay, so this helps you to determine the number of outcomes in the sample space. We did a similar thing for rolling 2 dice, where we drew the 6x6 table. So you realize the first activity, which is the first row of the die, has 6 outcomes, and the second row of the die also has 6 outcomes. So the sample space will be 36. Similarly here, the coin has 2 outcomes and the die has 6 outcomes. So to get the number of sample space for performing these 2 experiments, just make sure the 2 of them are being done. If they are not done, you don't have to do this. But once there are 2 experiments being conducted, doing this and doing this, to get a sample space for the entire activity we are doing, multiply the number of outcomes for each of them. Okay, so in this case, we are to get 12 elements here. So let's try and list all the 12. Okay, so we can work with a table if you want to, and I think that will be better since we are just starting. So you can have the outcomes for the toss of the coin here. So you can have a head or a tail. Good. Now you have the outcomes for the roll of the die here. So we have 1 or 2 or 3, 4, 5 or 6. Okay. Now let's match them just the same way we formed the 6x6 matrix. So we have H1, we have H2, we have H3, we have H4, we have H5, and we have H6. For this one, you can decide not to bring the commas in between. Remember, we did the commas because they were all values, so you writing 1 1 might seem 11. That's why we did it 1, 1 just to create a difference. But this is variables and our numbers, so you can just write H1, H2, H3. So here H1 will mean that getting a head after the toss and getting a 1 after the roll. H2 means you toss the coin, you get a head, you roll the die 2, you get a 2. H5 means that when you perform the experiment or the 2 activities, for the first one, you had a head on the coin and you had a 5 on the die. Okay, so that's the implication. So whenever you have 2 activities being performed, if convenient, you can apply this table thing and it will surely work, unless you can state it intuitively. That's what will happen when you grow some experience, but for now you can stick to this. So we have T1, T2, T3, T4, T5, and T6. Good. So this is a sample space. Whatever you see here is the sample space. And if you count them, they are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you know that you are correct after getting the 12. So after this, you can either decide to write it or probably leave it like that. There's no harm when you leave it like that. But if you feel you just want to rewrite it, you can do so up to the last one, which is T6. Okay. So any of them should be right. So this is the sample space for the experiment up there. Now let's move to the question 2, which says we should list all outcomes in event A. And event A says head appears and die shows an even number. So we are only interested in the head row. Okay, so we can have can we have H1? H1 means head appears and 1 shows, but 1 is not an even number. So we go to H2, then we go to H4, and we finally end with H6. Remember, we can't do anything with a T because T means that a tail appeared, and we are interested in head appearing, not tail. So for all the values for the tail, we wouldn't use any of them. Why? Because they don't have head in them. The event says a head should be present, accompanied with an even number. So we get only the 3 up there. This. Okay. So what is the number of A? Because we will be using it for the question 3 where we will find the probability. So A has 3 outcomes. Okay, the number of outcomes in A is 3. Good. So let's now do the question 3, which is to find the probability using the classical way. So we have probability of A equals the number of outcomes in A over the number of sample space. The number of outcomes in A over the number of sample space. This is the formula that we saw in the previous lecture. Please memorize it. Okay, so we have number of A, we had 3. We had H2, H4, and H6. In the sample space, we had it to be 2 times 6, which was 12. So the events of A, or the probability of A, is 1/4. Okay, as simple as that. So keep practicing problems like this, and you'll surely be a probability master, or let me say sorcerer. Okay, so let's move on to the next question we have, which says a coin is tossed. A die is rolled only if heads occurs. Let B be the event the die shows 5 or 6. I guess you are confused at this point. Then you can pause the video and look at the question critically and analyze it for yourself. Maybe you might not end up solving it correctly, but you can give it a good try. Okay, so let's revisit. A coin is tossed. So let me explain what is happening here. So first, you need to understand the experiment we are performing. If you don't understand what we are doing, like the activity we are performing, that's where things get, because you can't define the sample space if you don't understand what the person is doing. Okay, if I say I toss a coin and I roll a die, and you can't really capture what I'm doing, or you don't really get the experiment I'm doing, then you can never list the sample space. So understanding that experiment is very, very, very important. Okay, so a coin is tossed. So that one day we are certain you definitely toss a coin. But for you to roll a die, then you have to get a head from the coin that you tossed. So if you toss the coin and you are unfortunate and you get a tail, then you don't roll the die, you just leave. Maybe this is related to those casino games and those types of games where you do this just to win something. So this one, you toss the coin, you can only roll the die if you get a head. So if you don't get a head, that's where it ends for you. So let's first list the sample space, but you have to also take note of something here. There is a conditional, the second one is a conditional experiment. Okay, so you can't do the multiplication here. The second one we might do or not do. It's not always the case that you roll a die. No, you only roll a die if you satisfy the previous condition. So you can't do a coin has 2 outcomes and a die has 6. So you should expect 12 elements in the sample space. No. And the reason is that the second experiment is not always present. It has to follow a condition before it can happen. Okay, so it doesn't work here. Remember the previous slide, I said when you are sure that all the 2 will take place, then you can just multiply. But if one depends on the other, or one might not happen at all, don't multiply to get the number of sample space. Okay, good. So let's try and list this sample space. So this one we use no formula but an intuitive way to think through the question, and that's how probability behaves. General probability or the basics of probability have very few formulas. It requires you to think through. Okay, good. So let's list the sample space. So a coin is tossed, so we can apply the table here. It will be possible. Let's try and apply the table. Good. So we have a coin which has the head and the tail, and we have the die, which is 1, 2, 3, 4, 5, 6. Now, some of the cells will be empty, and you will see that. Okay. Now, when we come to the row for the head, after getting a head, can we get a 1? Yeah, that is possible. If you get a head, it's possible you get a 1. So we can have head and 1. Because when you get a head, you roll a die, and it might be that you get what? A 1. So H1 is possible. Someone might roll a head, toss a head and roll a 1. So that's H1. So it's possible. If it's not possible, we don't include it. Similarly, H2 is possible. In fact, H3 up to H6, they are all possible. This means that after you get a head, any number for the die is possible. Okay. Now, what happens when you get a tail? Is it possible to get a tail, to toss a tail? Yes, it's possible to toss a tail. But once you toss a tail, you cannot add any number. Once you toss a tail, you cannot add any number on the die. So this is where it becomes a bit tricky. So what is the sample space then? Is the sample space this? Some way you are 90% there, but that's not the entire sample space, because there's a chance that you might get a tail. Just that after getting that tail, we don't add anything to it. You see how it behaves? Once you leave the tail out, it means that no one can toss a tail, and it's wrong. Once you list the sample space and you write H1, H2, H3, H4, H5, H6, and you don't add a T, it means that you can only toss a head on the first experiment, meaning tail is not possible, and it's false. It's just saying that when you get a tail, you don't have a number attached to it. So tail stands alone. So in that case, our sample space becomes H1, H2, H3, H4, H5, H6, and a tail will be standing alone. So these are the possible outcomes. All these now you see, they are possible. Okay, H1 is possible, H2 is possible, H5 is possible, T is possible. Just that T1 is not possible. Once you get a tail, you can't get a 1, because you are not allowed to roll the die at all if you get a tail. but it doesn't mean that you can't get a tail. You can get a tail. Therefore, it should be we have the second question, which is to identify a simple event and a compound event. So clearly, from what we saw, so let me use E. So the easiest simple event is to say event of getting T. It's very, very simple. Just one outcome, T. Well, that's not the only simple event. Remember, simple event is just one outcome from the sample space. So looking at the sample space, you can choose any outcome or element there. Just that you have to be careful with your explanation, and you can't just write this alone. You have to write something. Okay, probability wants to see you writing, understanding, giving conceptual explanation to your mathematical work, not just mathematics. Okay, so the H1 means that the event of tossing a head and rolling a 1. Let me come again. H1 means that the event of tossing a head and rolling a 1. This is a simple event because there's only one way you can achieve this. There are no two ways you can achieve this. It's only one way, and the only way is to get head here and get 1 here. Aside this, there's no way you can get it. Or for you to easily understand and not confuse yourself, remember, event is one element from the sample space. So just pick one element from the sample space and include it in your set. Now you give a proper explanation to it. So the first one is the event of tossing a tail. That's the only way. You just toss the tail, nothing else. Or the event of tossing a head and rolling as a 1. If you say the event of tossing an H, that is incorrect, because from the sample space we don't have H alone, or we don't have head alone. So you pick any element from the sample space, then you form just a set with only that element, then you define it correctly. Okay, so that's a simple event we've seen. So for the compound event, you just pick any two of them, H1 and H2. So you can say the event of tossing a head and rolling a 1, or tossing a head and rolling a 2. Sounds technical, right? This event is saying that the event of tossing a head and rolling a 1, or tossing a head and rolling a 2. So you pick 2 elements from the sample space and you define them correctly. Okay. Another event could be H1, H3, H5. You don't have to talk much. So you can say the event of tossing a head and rolling an odd number. See how beautiful it is? The event of tossing a head and rolling an even number. Hey, sorry, an odd number. Okay, so head 1, head 3, head 5, they are all events satisfying what I just said. Tossing a head and rolling an odd number. You get this. Or you can even redefine this as the event of tossing a head and rolling a number less than 3. See how it is? Not a single way to. That's why you need to explain or write something down to make your answers valid or complete. So this one, someone might say the event of tossing a head and getting a 1 or tossing a head and getting a 2. The person is right. Someone might also say the event of tossing a head and rolling a number less than 3. So in that case, it's not just one way that we can satisfy that. Someone can get head and 1, is satisfied. Someone can also get head and 2, is also satisfied. So once there are more than one way to satisfy the condition, we say that is a compound event. Okay, so just pick any element from the sample space and write them nicely. Good. So now we have the probability of B, and we know that probability is the number of B over the number of sample space. Oh, we didn't list the number of sample space, but I can still remember. We have H1 to H6, which is 6 of them, plus a T. So the number of sample space that we had was 7. You can check from your book if you wrote it down. Now we need to define what's the event of B. So the B says that the die shows 5 or 6. It doesn't mean you should write 5 or 6, because 5 or 6 is not even in the sample space. Any event that you write should be from the sample space, should be from the mother. And we don't have 5 or 6. Okay, so it's a bit tricky to get you. Actually, it means that B is equal to H5 or H6, because you can only roll 5 or 6 if you've passed the tossing. When I say pass, I mean if you've had a head on a toss, that's the only way you can roll the die. So getting a 5 or 6 means that you had a head and you went on to get a 5. Let's take this scenario where we say that, okay, you win this game if you roll a 5. If you roll a 5, you win this game. You win this game. Does it mean you just go there and take the die and roll it and get a 5? No. You have to do something before you can take the die. And that thing that you have to do is to get a head before you can proceed with a 5. So generally you might see the thing being just a 5. But once there are things preceding the 5, you have to make all of them available. So this event of B being 5 or 6, since 5 or 6 is not in the sample space, and the only 5 or 6 there is H5 and H6. So getting a 5 means that you already had a head. Getting a 6 means that you already had a 6. So even if the question does not mention that the B is the event of getting a head and later getting 5 or 6, once it's silent about the head, it's automatically implied, because you can't get 5 or 6 without getting a head. Okay. So in a case where head or tail either you get head or you get a tail, you still roll the die. That one, the question will specify that B is the event of getting a head and a 5, or getting a tail and a 5. But once head is the only way, it might decide not to even mention the head. Just say 5. And you should know that to get a 5, you have to get a head before. Okay, good. So the number of B is 2, meaning there's only 2 ways to satisfy B. That is, first of all, getting a head and coming to get a 5. Yeah, you've satisfied the condition. Or getting a head and coming to get a 6. You've also satisfied the condition. So the number of elements in B are 2. Okay. So in that case, the probability of B, which is the number of B over the sample space. This is the correct answer. Okay. This is the correct answer to the question. Alright, so you can take your time, rewatch if you didn't really get it, or you can also instead turn a new page and try if you get the 2/7, and make sure you truly understand it. If you don't, reverse the video and re-watch it. Okay, so we move on to the next question that we have. So this is also a very nice question. 2 dice are rolled. Let C be the event. The sum of the dice is divisible by 6. The sum of the dice is divisible by 3, not 6. First of all, list all the outcomes in C, and secondly, find the probability of C. So we are to do justice to that. So let's look at what is happening. 2 dice are rolled, and 2 dice are rolled is just like the example we saw, where we have 1, 2, 3 up to 6. We have 1, 2, 3 up to 6, and we had 36 outcomes in the sample space, just as what we saw in the previous lecture. In other words, to get the sample space, you can multiply the outcomes from the first die, which is 6, times the outcome from the second die, which is also 6, which gives you a total of 36. Now so with this one, you can draw your table, or you should actually draw your table, and now use your eye to visualize which of them is divisible by 3. Okay. Alternatively, you can follow this approach, but in all, I would advise you draw the table, because with this approach, you are thinking through of which, with some low level of experience, you might end up leaving out some of the events. Okay, so it's best to draw the table and visualize which of them is divisible by 3. But my screen might not permit me to do that, and it's also important to show you this way so that you can be a little versatile as to what you want to use. So we have the sum is divisible by 3. Obviously, 1, 3 should be parts. Sorry. 1, 2 instead. And we know the sum of 1, 2 is divisible by 3. The second one will be what? 1, 3 is out, 1, 4 is out, 1, 5 is in. 1, 6 is out, because 1, 6 gives us 7. Now we move on to 2. 2, 1 is definitely in, because 2, 1 gives us 3. 2, 2 is out, 2, 3 is out, 2, 4 should be in, because 2, 4 gives us 6. 2, 5 is also out. 2, 6 gives us 8, which is also out. Now we move on to 3. 3, 1 is out. 3, 2 is out. 3, 3 should be in. 3, 4 out. 3, 5 out. 3, 6 should be in. Okay. Now we move on to 4. So for where with which we can look at what is previously there and easily determine which ones are in and which ones are not. So when you look up here, you notice that 4 only appears once. Okay, so there might be the chance that you only have 4, 2 and nothing else. Let's verify that. 4, 1 gives us 5 is out. 4, 2 gives us 6 is in. 4, 3 gives us 7. 4, 4, 8. 4, 5, 9. Good. So because you are not on 5, so let's just maintain the manual way. Okay. So we have 4, 2. And finally 4, 5. So with 5, 2. With 5, we can have 5, 1 as we can see up here, and 4, 5 as we can also see here. Sorry, 5, 4. And for 6, looking up here, we only have 3 and 6, so we will have 6, 3. Good. Sorry for making it messy. So this is the reason why I'm saying the table will help you out, because that one you can easily tell which ones will be in and which ones will be out. Even as of now, I don't know if I've left some out. Yes, but either ways, the goal is for you to understand, and I believe you are doing that. Good. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But before we move on, let's do some quick cross check if we've left anything out. 1, 1, 1, 3, 1, 6, 2, 2, 2, 3, 2, 5, 2, 6, 3, 1, 3, 2, 3, 4, 3, 5, 4, 1, 4, 3, 4, 4, 4, 6, 5, 2, 5, 3, 5, 5, 5, 6, 6, 1, 6, 2, 6, 4. So okay, so I believe this should be right, and we're having the number of C to be 11. Oh, I didn't get 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sure. So the number of C is equal to 11. Why do we need the number of C? We are using the number of C to solve the question 2. But for the question 1, it's just to list the outcomes. Okay, good. So because you are told to list the outcomes, even after drawing a table and visualizing which ones are in C, you have to come and state C again as a set. The table is just to help you identify which ones will be in C. But if you feel to waste some of your time and you can easily think through and do it manually, that's also good. But in all, make sure you list it as a set. Okay, good. So probability of C will be the number of C over the number of sample space. The number of C we had to be 11, and the number of sample space we know to be 36. Okay, so that's how to correctly determine the probability of C. Okay, good. So we proceed to the next question we have, which is 5 coins are tossed. 5 coins. It's getting intense. Let D be the event exactly 2 heads appear. First, list all the outcomes in D, and second, find PD. Okay. So this one we can't use a table because the experiments are not 2, they are 5. So you can't use a 2 by 2 or a table with a row and a column. No, because they are 5. So this one you have to be sharp. So let's first determine the sample space, because that will help us get what D is. Okay, because we are picking D from S. So once we know S, getting D might be a little bit easier. So we can determine the number of S. Wow, this is really huge. Might be difficult for me to list S here, and even for you on the exam day. So you can skip S for now and just make sure you can correctly determine the event D. Okay, so the reason I'm saying S is very huge, remember the experiments are 5. Each of them produces 2 outcomes. Don't go and do 2 times 5. I said multiply the outcomes for each experiment. When you toss the coin for the first time, the outcomes are 2. The second one, possible outcomes 2. The third one, 2, 2, 2. So each of the experiments or each of the toss results in 2 different outcomes. Could be a head or a tail. Okay, so don't go and do 2 times 5 and say they are 5 coins, so times 2. I said it's the outcomes for each toss, multiply them, so 2, 2, 2, 2, 2, 2, which is 2 exponent 5. Okay, so 2 exponent 5 giving us, is it a 32? Yes, that's 32. So listing the 32 outcomes might be a very, very huge task. That's why I'm saying we can skip the S for now and just correctly determine D. Okay, so let's see if we can easily and correctly you can easily wait. Yeah, this. Let's see if we can correctly determine D. So D is saying 2 heads appear. So after tossing the 5 coins, we are expecting to get exactly 2. So 2 out of the 5 coins shows heads, and the other 3 shows tail. Okay, so that's how you can do that. You have to apply the distinctive concept that we did the last time. So the first one can be head, the second one can be head, and the remaining ones can be tail. Or the first one can be head, the second one can be tail, and the remaining ones can be head. Sorry. Remember, we can have a maximum of 2 heads, so it's still that I was saying. So the first one can be head, second one tail, third one head, and the other 2 are tails. Or first one head, T, T, H, and T. So it's like one head is standing and the other one is moving. Or head, tail, 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 head. Okay. So we also push the head that was always standing at the first position, we send it to the second position. Okay, and now we move the other one. So T, 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 then T still standing there. Then we float the other. Then T, H, C, C, H. Now we move this T that's always standing at the middle to the third position. So we have T, T, H, then H, T. Then we have T, T, H, T, H. Now we move the H always at the third position to the fourth. So we have T, 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 H, H. And that completes the listing. In fact, this listing is not really easy. Yes, ideally I should have made it 3, but a 5 is also not bad. Okay, so just make sure you include all outcomes where the T are 2. Okay, make sure they are all in here. And the style I used was that let me teach you one more time. I first place one H here, then I'll be floating the other H. Okay, H. So I'll move this H to the third position, and I'll move it to the fourth position while the other one remains at 1. And I finally move it to the 5th position. Then thereafter, I'll bring this H here to the second position. And when you do that, don't start this at 1. Don't bring this to 1 like this, no. If you do that, it will be the same. It will be the same as this. Okay, so the one that you are floating should always come after the T, the standing one. You get it? So once you move this guy to the second position, the floating T should start from the third. Okay, as easy as that. Good. So after getting the HCTH, I move this first guy to the second, and I have to put a T here. Now the floating guy starts from here, TT, then it moves to TH, TH, T, then finally TH, T, T, H. So when it reaches the last point, then we move this standing H, okay, to the third position. So we have T, T, H. Okay, then the floating H comes here and moves here. Then we have T, T, H, then T, H. Okay, now we move this standing guy to the fourth position. So you have T, 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 H. Then the floating guy follows. So maybe it's good I brought the 5 so that when you meet the 3, it will be simple. Maybe I should also do the 3, but before, let me count this. So because we are going to use them. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 of them. Good. Now let me teach you how to list the 3 outcomes with 2 being heads. We can have head, head, T, then this head moves here. So once it's at the end, we send this guy to the second. So for this, we have this outcome. Okay. Good. So practice with the 4 and you'll definitely be familiar with it. Now, let's proceed to question 2, which is find the probability of D, which we know to be the number of D over the number of sample space. So the number of D we found to be 10, and the sample space is 2 times 2 times 2 times 2 times 2, or 2 raised to the power 5, which is 32. Okay, so that's how to solve this particular question. So we've seen how we listed all the outcomes in D. D has 2 heads, and I showed you a way you can always get through with that. Just keep one and be floating the other, and make sure the one you are floating doesn't come behind the one that always stands still, else you get 2 outcomes being the same. So once you do that, you find the number of outcomes in D, which we had to be 10, then divide by the sample space, which I taught you to multiply the outcome for each of the toss, which is 2, 2, 2. So we have 36. Okay. So that's it for this question. We move on to the next one. So a bag contains 8 red, 7 blue, 6 green, and 4 yellow marbles. We are drawing one. First, we should calculate or find a probability of selecting a red marble. So, probability of red marble is equal to what is the number of red marbles over what is the total sample space. I remember the example that we had 2 red marbles, 3 green marbles, and 1 blue marbles. I told you the sample space should be the total number of items, which we had to be 6 in the previous example. We had 2 red, which I labeled as R1, R2. 3 green, which I labeled as G1, G2, G3, and 1 blue. And I told you the sample space is the total number of outcomes, which is 6. Okay. Similarly, we have here that the number of sample space is equal to the total number of items, which is 8 plus 7 plus 6 plus 4. The number of sample space, not the sample space itself. To list the sample space, you should write R1, R2, R3 up to R8, then B1, B2 up to B7, G1, G2 up to G6, and Y1, Y2 up to Y4. That's the total sample space or the set for sample space. But for the number of sample space, you just sum the total, the items for each color, so that you get the total items in the bag, which will give us, this is 10 plus our 13, sorry, our 15, it gives us 25. Okay, so we have the number of sample space to be 25. Now, what is the number of red marbles, which is 8? So, kind of easy question. And it is intuitive. If you have 8 red marbles in a total of 25 marbles, what is the probability of getting red? Or what is the chances that red will be selected? It's 8 over 25. Okay. It's the total number of red balls, which is 8, over total number of red marbles, which is 8, over the total marbles in there, which is 25. Okay, good. So we talk about this B, probability of not selecting a green marble. Remember, complementary events or complementary probability, which we denote by P, E, C, or P, E, bar, or P, E, prime. When you see these three items, this is a C. You see these three items in probability, they mean the same. And what they mean is that the probability of not getting E, or the probability of E not happening, or the event is not E, is a different thing. Any other thing aside E. Okay, good. So that's what we are being tested for this particular question. So we are asked to find the probability of not selecting green. Not selecting green. This is how to write it. Not selecting green. And we saw in the last lecture that not selecting green is equal to 1 minus actually selecting green. Because note that we saw that P of green plus P of not green should be equal to 1. P of green plus P of not green should be 1 from the previous lecture. In that case, if you want this, the P of not green is 1 minus this, because we will move this to this side. Okay, so that's the probability of not green. So let's go ahead and find probability of green, because it is easy to do that. It's just the number of green over the number of marbles. Okay, so I'm saying probability of green is equal to number of green over number of sample space being 25 and green being 6. So there's a probability of green, but we are asked for the probability of not being green, which is 1 minus green. Okay, which is 19 over 25. Okay, so the probability of not being green is 19 over 25. However, someone might also count the total number of balls that are not green. That is not wrong at all. Just that for some questions that you might meet, you have to definitely apply the complementary. So even though there are instances where you can see your way through by not using the complementary event theorem or whatever, some questions, the question is structured in a way that without knowing that probability of the not getting is 1 minus getting the G. Without knowing this, you cannot proceed. So in as much as you can just count the number of balls, that's the number of marbles that are not green, and go ahead, because when you add 8, 7 and 4, these are the marbles that are not green. When you add them, you will get 19. So someone might say, okay, 90 over 25. That is correct. But in some cases, or in certain questions, of which I'll try and bring one, there's no way you get through with the question without knowing the complement. And complementary events runs through. You go to law of total probability, Bayes theorem, and all those stuff where we apply complementary probabilities. So make sure you get the concept here and know how it is applied. So in this question, you can just find the probability of being green marble, which is directly 6 over 25. Then you find the probability of not being green as 1 minus being green, which is 1 minus 6 over 25, which is 19 over 25. Okay, good. So now we proceed to the last question for the day. So this is the last question that we have. Then we end the lecture successfully. So we have a coin is tossed and a die is rolled. 2 events happening. Let E be a tail appears or the die shows a 6. A tail appears or the die shows a 6, which is trying to be technical. But for this particular question, we can list the sample space and that will be easy. And note that all the 2 activities are being performed. It's not like the previous one where you can only do the second one after passing the first one or after successfully doing the first one. For this, we are doing all the 2. So let me put my coin here and let me put my outcomes for the die here. So we have H1, H2, H3, because we are doing both of them, so they can all happen. T1, T2, T3, T4, T5. For this question, it's not like you get ahead before you can roll the die. No, whatever you get, you can. So you can get a tail and you get a 3. You can get a head and get a 5. Get a this. So they are all possible. So this one we don't make any restriction. Now, what is E saying? E is saying that a tail appears or the die shows a 6. A tail appears or a die shows a 6, or the die shows a 6. Now look at this. So this is our sample space. This is what we are working with. Oh, that's unfortunate. Oh, the software I'm using, I accidentally tapped. Oh, that's unfortunate. Well, let's quickly do it again. I'm sorry about that. Let me quickly do it again. So H and T, 1, 2, 3, 4, 5, 6. H1, H2, H3, H4, H5, and H6. T1, T2, T3, T4, T5, T6. Good. So I was saying this is the sample space. Okay, this is a sample space. So you ask yourself, look at E. It still appears or the die shows 6. So from the sample space, where are tails appearing? Or let me say, where are tails appearing? Tails are appearing here. Can you see that? So a tail appears. So once you toss a tail, you have succeeded. And these are a tail appearing. So all these 6 outcomes are in E. So E is T1 or T2 or all of the T's. In statistics or probability, if you can't list all the outcomes, you can use an ellipse, this 3 dots. It's not necessary that if you have 36 outcomes, you have to list all the 36. No. You can list the first 4 or 5, use an ellipse, and list the maybe last 2 or 3. It's not necessary to list all the 36 or 54 outcomes. No. Do the first 5 and maybe the last 3. If it's just 12, you can do the first 3 and do the last 2. Okay, just to use an ellipse to mean that T1, T2, dot, 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 T6. It means T1, T2 up to T6. Yes, that's the implication. But if your lecturer doesn't also allow that, don't do that. So you have to always clarify from him or her whether he or she supports that or not. But generally or basically in probability, using ellipse to list outcomes is allowed. Now, we say E should contain a 6, a tail, or a 6. Okay, so we have T1 up to T6. Now, what do you think? If someone gets H6, this guy, do you think he or she can fall under E? E is saying get a tail or get a 6. Get a tail or get a 6. So if you get head from the tossing, it doesn't mean life has come to an end. You can still satisfy E by getting what? A 6. The question didn't say a tail appears and a 6. It would have been different if this thing, the all changes to end. End means that get a tail and get a 6. That one is just T6. A tail and a 6. That one is tail and 6, T6. That one, like all these T1, T2, they wouldn't appear because it says tail and 6. But this one says tail or 6. So if you get tail, success. If you get 6, success. That's why you are seeing T1, T2, T3. So if you get a tail and 1, once there's tail, that's a success. So I'm saying we have to add the H6. This is because H6 also contains a 6. A tail appears or the die shows a 6 or it shows a 6. So aside tail appearing, once the die shows a 6, we don't really care about what the coin is saying, whether the coin is head or tail or stomach or whatever, we don't care. Once the die shows 6, E has happened or has occurred. So the correct E will be T1, T2, T3, T4, T5, T6 plus H6. Why? Because it says tail or 6. So these are the tails and this is the or 6. For T6, the meaning that you want to say hokra, like you've spotted the hokra, you've gotten the tail and you've gotten the 6 too. So that one is extra. But we also have to include H6 because that one you also have a 6. So this is the E that we are interested in, a tail or a 6. So meaning each of the outcome, we should either see T or we should see 6. If we don't see T or 6, we don't include them. That's why we didn't add the other elements in the sample space. So now, what is the number of E? Because we will use this to find the probability. So The number of E is 1, 2, 3, 4, 5, 6, 7. Number of E equals 7. Now, the probability of E is the number of E, which was 7, over the sample space, which is 2 for coins, 6 for die. 2 for the coin has 2 outcomes multiplied by the 6 outcomes from the die. So the number of E, the probability of E is the 7 that we had over 12. The 7 that we had over 12. Okay, good. So you so you just correctly determine the event E, list all the elements, then you proceed to find the probability. Okay, so that brings us to the end of today's lesson. I hope you enjoyed it. If there are any questions or anything that you feel I didn't do it in a way that you were expecting, or you have any alternative way, or you feel there's something wrong with what I was saying or explaining, drop it in the comments. The next time we meet, we will address those issues before we proceed to the main lecture or lesson for the day. Have a nice day, and I'll see you in the next lecture.